I'm going to be talking about Haskell and imperative programming. I'm sure everyone knows what imperative programming is. How many people know what Haskell is or have heard of Haskell? Okay, like a handful. Okay. How many people know what types are, like strongly typed programming, strongly typed functional programming? Okay. Okay. So we can keep it simple, but go into a little bit of detail somewhere. A little bit about myself first. My name is Anupam Jain. I work for a company called S&P Global, where we build functional programming based web applications, primarily for financial services. And we use a lot of functional programming in both the front end and the back end, right? So I'm going to be talking about this language that we use called Haskell. And yeah, okay, before I continue with that, we have a functional programming NCR meetup group, right? So anyone who's interested in whatever I say today, like, please join this, right? We have discussions around functional programming and things related to functional programming. All experience levels are welcome. There are a bunch of ways that you can join. Telegram group is where we have most of our discussions, right? The group is called FPNCR. You can, if you search for it, you'll find it. All right. So this is what we're going to be talking about. For people who are familiar with the imperative programming, but not strongly typed functional programming, these are the benefits, right? So we get type safety, which eliminates a large class of errors, and we get a lot of reduction in boilerplate, and we get zero cost code reuse. If you're gonna take something away from this talk, right, this is what we're gonna talk about. How do we reduce boilerplate with functional programming? How do we reduce cost associated with abstractions, right? We're gonna talk about zero cost abstractions with Haskell. A thing about functional programming before I start, for people who don't know, strongly typed pure functional programming means there are no effects, right? Most of your code is going to be pure, and effects are done through some mechanism, which is in Haskell, it's monads, right? So I'm not going to be talking specifically about monads, but monads are basically imperative programming in Haskell. You can think of it like that, right? So what is imperative? Imperative is when you have a bunch of operations where the order of operations matter. So if you say x is equal to x plus 1, and then you say print x, what gets outputted depends on whether x is equal to x plus 1 is executed first or whether print is executed first, right? When we talk about functional programming, it means that the order of execution does not matter. If we say x is equal to 1, y is equal to x, print y, then you can do it in any order. It's going to do the same thing, because what's going to happen is if you try to print y first, it'll first ask the program what is y. Then it'll figure out y is x. What is x? X is 1, so it'll print 1. Irrespective of which order you execute these in, it will print the same thing. So we do pure functional programming, which means that the order of operations does not matter. So how do you do this in imperative programming? So this is imperative. It looks pretty simple, right? Let's say you have a program that does whatever you want, right? And you wanted to order a pizza and then also launch nuclear missiles at something, right? So how would you do this? So the program would be like, subservient robot, right? So it'll ask you, okay, do you want a pizza? You say yes or no. If you say yes, it's going to order a pizza for you. It's going to ask you, okay, do you want to launch nuclear missiles? You say yes, it'll launch missiles. Here, you really don't want to do these out of order, right? You don't want to say that, okay, you don't want the program to say, do you want a pizza? And you say yes, and it launches nuclear missiles. You definitely don't want that to happen. So this is imperative code. Let's first see how this looks in functional programming. This is Haskell code, right? So this is actually Haskell code. This is how you would write it. So the functions write and read don't exist. They're called put, stir, ln, and so on. I'm not going to talk about the details here, but this is how you would write it. You have something called do, right, which you can think of as a block of statements, right? And these statements, whenever you write do, they are executed in order. Order is significant. So this is how you would do imperative programming in Haskell. This is pretty simple, right? So some details about the syntax here. When you have this backward-looking arrow, that means that you're assigning to a variable. So here you're saying write something to the console, and then read something from the console and assign it to can order, right? We're gonna assume that this is a Boolean, not a string, okay? So we're getting back a Boolean. And again, if when is like an if statement, if cannot or is equal to yes, then do something. Oh, here it is a string, but later on I'm going to assume that it's a Boolean. Similarly like that, right? So this is Haskell. This looks exactly the same. This has the same problems that any imperative code has. But how does it work in actual functional programming? Haskell, so I'm not going to go over details of this because we don't have a lot of time, but this is what Haskell actually compiles. Do notation is just a syntactic sugar over functions, right? Everything is functional in Haskell. So this is what the functional notation looks like. We have a function called bind. This double arrow equal to is called bind, right? So you can think of it as one giant expression that makes lots of functional calls. So I just want to show you this, that this is what it actually compiles down to, right? This is what the syntax looks like. You have lambdas in Haskell. So anytime you see slash and then a variable name, and then this is very similar in other languages now, right? You have lambdas in lots of other languages, including Java, right? So this is what syntax for lambdas looks like in Haskell. And then this is what the bind operator looks like. It takes an effect, for example, write something to the console, and then it takes a handler, whatever is the output of that effect. So in case of writing something to the console, there is no output. In case of reading something from the console, a string is an output, right? So you have a handler, and effectively, you're not making statements in order. You're calling one function that composes the effect and the handler together, right? How many people are familiar with JavaScript and Node.js based programming? This is called callback based programming, right? You, instead of getting a result back and then doing something with the result, you pass a callback. You say, when you get a result, call this, and this will figure out what to do next. So this is how things work in Haskell and in pure functional programming. This is how we get things done, right? How do you do imperative stuff? Okay, so this is what it basically means. You say, read something, and then you get the variable, and then you pass it. So this chain, this train of operators, that's what it means, okay? You're saying an effect, get a variable in a lambda, and then do something with that variable. That's going to be the body of the function. And then here, you can do something more. So again, you can say read again and get can launch nuclear missiles, do something with it. So you can keep on nesting it infinitely. So that big expression that we saw earlier, that's basically chaining of this a bunch of times. But it's still one function. Okay, so now we want to separate out the two parts of it, right? We want to refactor the code. It's very messy right now, right? We want to make sure that if the program asks us about pizza, then it executes something about pizza. It doesn't try to launch missiles, right? So the way we do it is we separate out the two things. Again, this is very imperative refactoring. This is what you would do in a normal imperative program. So you would write a separate function, and I should have probably written do notation here, but it basically uses the same syntax, right? It effectively says that, you know, do you want a pizza? And then this is the only thing that's different. Instead of when I'm using I'm using if-else statements. The thing that's different about pure functional programming is that you need to have an else statement always. You can't leave it blank. So here we are saying do nothing. Pure is like return. So we're saying return a blank value, right? In case that you don't want to do anything. Similarly, we have this, right? You would notice that launch missile doesn't have brackets, right? Because in Haskell, there is no difference between calling a function and referring to a function. A function is a function, right? It's just data. So if when you say launch missiles have been launched at that point. Okay. And then you can compose those two functions together. Again, I'm using the same syntax. I'm saying do this, right? The result of this I don't care about because there's nothing coming out of handle pizza. The handle pizza function has already handled everything, right? It's ordered the pizza if needed. And then handle missiles. Again, ask about the missiles, launch them if needed, right? So this is how you compose things. This is like normal statements, normal function calls. Okay, now we look at some things that are different. What is different? So the type of this is an IO unit. Unit is no return value, no significant return value. So there are two things here. One, that it returns a unit. It cannot return anything else like Boolean. Second, that it's an IO operation, which means it's imperative. You cannot use this inside something else, right? Inside a pure computation, without that also being effectful. So this is how functional programming has a pure core, which is here, and all the effectful computations are surrounding that pure core, right? And then all the branches, as we saw, must have the same return type, right? So when people will talk about imperative programming in functional programming languages, they will talk about these things that, okay, why is functional programming great? Because you can have an impure computation, but it can't mix with pure computation. And that prevents an entire class of errors and less bugs and so on. But to me, all this talks about is what you can't do with functional programming. Okay, so I don't want to focus on that. I want to focus on what you can do with functional programming, which you probably can do with imperative programming also, but it's going to be an order of magnitude more difficult, right? So I'm going to talk about how we refactor that bit of code to make use of functional programming constructs even with imperative programming. So we're not going to go into pure functional code. We're going to stick to imperative, and I'm going to show you how to refactor that to be more functional. That's the purpose of this talk, right? We're going to stick to things that you know. This is what it looks like right now, right? Ask any new Haskeller, new functional programmer, stay away from side effects, right? This is you, the pure code, stay away from all effects outside, right? We want to get away from this perception. At the end of the talk, you'll do better than this. So yeah, just the motivation behind this talk was that Simon Peyton-Jones reportedly said that Haskell is the world's finest imperative programming language. If you want to do imperative programming only, then also Haskell is the best option that you can have. So I'm gonna show you why, right? That's the talk. Okay, so let's say our requirements are changed. If we don't have pizza, we don't feel like launching nukes, right? So we want to now have a condition that if the person did not order pizza, then don't even try to launch nukes, right? How would you do this? You will add an if condition in this block, right? You would say, if you ordered a pizza, so you already had an if condition, you would return a Boolean that indicates whether pizza was ordered or not, right? And then we can use this inside our simple function, which earlier just did handle pizza and handle missiles. Now handle missiles will first check if pizza was ordered, right? So this is the first thing, that you can return values from inside imperative code. This is an important thing. Right now it seems simple, but we'll go into more details here. Okay, now let's say we want to do something different. We want to, yeah. So what we want to do is ask the user 2 questions and then do all the effects together at the end. So earlier, what our code did was it asked if the user wants pizza, right? And then ordered pizza if so, and then did the rest of the processing. This is actually a very bad idea because the user may take a long time to do different steps. We don't want to hold up our effect processing until that time. Or conversely, the user may say, okay, do this, do this, do this, do this. We want to have more control over what effects get processed at the end, right? So we want to dissociate the act of asking the user for information and actually acting on that information. We don't want that to happen at exactly the same place, right? So how do we do that? We're again back to our earlier code where earlier we had launching missiles and ordering a pizza in separate functions. Now we can't do that anymore because they're now intermixed. We want to ask 2 separate questions, collect the results, and then perform 2 separate effects, ordering the pizza and launching the missiles, right? So this is what, again, this very simple imperative code. How many people do not understand this? Or do understand it? How many people do understand it? Okay. Okay, great. So most of you understand it. That's good. So again, I'm going to explain this. So you ask a question, store the result of that question in this variable, ask a question, store the result in this variable, and then you do the 2 effects together, right? And you can potentially imagine doing other stuff in between, right? Pretty simple code. But now we have, as I said, we have lost the separation between ordering pizza and launching news. We don't want that. So how do we do it? We want something that's very, we want like a pony, right? We want to be able to define complex flows with some user input and some effects, but we want to define them separately, right? We want to be able to compose these flows, but without any boilerplate. We don't want to do a lot of negotiation around that. And then we want to be able to put these things together and have the functionality we desire, which is asking questions first and then having effects later. How do we do this? I want you to think about how would you do this in imperative programming, right? How would you do it in your favorite language? Try to do it. It's obviously doable, but what technique would you employ, right? So this is what we want. We want something like this. Let's create a skeleton of the functionality we want. We want to define a handle pizza that includes everything there is to know about asking the user about pizza and actually ordering a pizza. We want to create a function called handle nukes, which again knows everything there is to know about asking the user for nukes, actually launching missiles, right? And then we want to somehow compose these things together. This is the desired functionality. How do we do it? As I said, imperative code can also return values. It can also return more imperative code to execute. Okay, so we need to separate the act of asking a question from the act of actually ordering the pizza. So what we do is we write our code in such a way that you first ask the question, which is an effect, and then you return the remaining effect. Here we are returning this, which is an effectful computation. You can see how little code you have to write in Haskell to do that. There's no wrapping, unwrapping. It's very, very clear, right? You want to return a function, you want to return an effect, you can just return it. Everything is first class, right? Everything is a value or data. So here we are saying that get the user input and then return something which, if the user had answered yes, right, it will order the pizza. We can just do that. This is a closure because the result of the user input has been captured here. The effect we return can always refer to what the user input was, right? So this is a closure. Again, these concepts are there in every language, right? But you can appreciate that this is still imperative. I'm not going to go into pure functional techniques. Okay, similarly, we write a similar thing for nukes, right? And then we can compose them together. How many people can understand how this would work then? From what we've learned so far. It seems very simple, but this does what we want it to do. Hermine does.
With the first two lines, we are actually turning our lambda expression, or we can say higher order function.
Right.
And it's actually lazily evaluated when we mention like pizza effect within a third or fourth line, it actually executed because.
Perfect. Exactly. This is what happens. When we did handle pizza, it created an effect to be returned, but that effect is not executed in the spot. It just is returned. Effects are first class values. They're values. If you never actually executed it inside a do block, nothing will ever happen. Right? So here, but handle pizza does have an effect, which is asking the user for input. It captures the input into a closure and returns that as an effect. And that effect can, at any point of time, be scheduled. So this is how you would do it in Haskell. Simple, straightforward code. Okay, I still don't like it. Okay, too boilerplatey. What if I have like 10 effects and then I have to, this is very simple, right? Why do I have to do that work? Why can't the computer do it for me? Right? So here I'm saying, okay, first I have to execute all of them, get the effects, then sequence all of them in a line. My code is becoming longer. If my code is longer than 2 or 3 lines, I don't like it. Okay? No function should be longer than 2 or 3 lines. Okay, so what we want now is something that just allows us to compose these things together. I want to say, do handle pizza, do handle nukes, do whatever else, and that's all I want to write. I don't want to get stuff out of it and execute them separately. Again, think about how you would do it in your favorite programming language. Right? How would you implement something like this? I want no boilerplate, the minimal thing possible. And of course, I want to be able to say that, okay, if I can compose a list of effects, then I also want to be able to say no effects, right? So I also want something called empty effects, which basically stands for an empty list of effects. This, for people who are familiar with functional programming, looks like a monoid. A monoid is something with an empty value and a way to combine 2 values together. And we decide, as programmers, what that combination process looks like. Okay, so it's like a class method in Java. And so you can call that class method, then depending on which subclass has overridden it, you get that behavior, right? So it's like that. So this is how the class looks like. I'm not going to go into details of what the syntax is, but basically this is the operator that it defines. Unlike Java and many other object-oriented programming languages, you have to define class methods on an object. Not so in Haskell, right? You define an operator that can take any number of arguments. Here we've defined a binary operator that takes handle pizza, handle nukes, right? It takes 2 effects, and we want that this processing, which we will define, does the right thing. It composes these 2 things together in the right way. Luckily, this code is already written for us. We don't need to do anything to get this done. So it's true. So if you define your code like this, and you monoidal join them together, that's called mappend with the two angular brackets. This will already do what we want. How did we come to that state? So I'm going to show you what the Haskell code looks like. We don't have to write it. It's already written for us. Forget about the empty part. Not going to go into details of that. When we join two effects together, what do? We run the first effect, get the result. We run the second effect, get the result. And then now ours was a special case, maybe we're returning two effects again. But luckily, what it does is it calls the monoidal mappend operator again on the return values, which again calls this with the inner results, right? Again executes the first one, the second one, right? And then it doesn't return any specific result, so it doesn't do anything. Monoid for unit is just unit. Like no values when joined together become no values. This is very logical code, right? That's why it's in the standard library. This is the only way you can do monoidal append on effects. There is no other way to do it. You can only do it when the things that you're returning from those effects also are monoids. That means they also have this operator defined. And then what it does is it gets the results out of those effects, which means executes those effects, and then joins the result values together and returns that. This is the crux of the presentation. I want to make sure that everyone understands it.
So Haskell IO is also monoid. It supports that.
IO also has a monoid instance, yes. That's the technical term, that it has a monoid instance, right? Which you could say it implements the monoid interface. That's the way a Java programmer would say it, right? The important thing here is that a lot of these functionalities are already defined in the standard libraries for us. And they turn out to be very general. Most of the time, you would try to think that, okay, I need something like a monoid for IO, but what if I don't want this? You will never want something other than this. If you want something other than this, you're doing something wrong, right? It's a bug. Try to figure that out. Yes?
So in the previous code we have, so we have two effects, F and G.
Yes.
And we are defining the mappend to it.
Yes.
And we abstract A and B, and then we call it again.
Yes.
So how are we sure that whatever effects I'm calling mappend on, whatever the A and B are, they are also monoid?
Yes, because we are, okay, so this is what that line means. I glossed over it. Basically what I'm saying is that you can define IO A is a monoid if A, the value that it returns, is also a monoid. This is a precondition to defining that class. You can have preconditions like this in Haskell, and they're all over the place. Okay? So, does that answer your question? We are basically specifying that this is only valid if the A is also a monoid. Right? This is a precondition. Any questions on this further? Because this is an important point. We're going to go into slightly more detail after this, refactor it a little bit more. So if there are any questions, please let me know.
So I guess what I know, like monoid is actually help us to combine the same type of things into
Yes.
one, right?
Yes.
So if we have a multiple function calls like f, g, h, i, j, k, l, m, n.
Yes.
So in that case, so still we need to define like that backside arrow within that arrow.
It's so monoids are associative, which basically means that if you do A mappend B, and then you take the result and do mappend C, that's the same. So the order doesn't matter. You can do A mappend and then in brackets do B mappend C, right? So you can take any number of elements, do mappend together, and they will always give you the same result. They're guaranteed to do that because of laws, right? So every class in Haskell needs to have laws that says that this is how we expect it to behave, and they're mathematical laws, right? So one of the laws for monoid is that it needs to be associative. Another law is that if you take an empty thing and mappend it with anything, it just gives that thing back, right? So that's also a logical law. All right, so moving on. So this is, I already explained this. It's already a monoid. You basically first get the results, and then you join them together again, which is again IO, an effect, and it does the same thing. So this is what the final code looks like. You basically create a new effect, handle pizza and handle nukes, by joining them together. Monoid, when it joins two things together, it gives you a thing of the same type. If you join two ints, you add them, you get an int back. You cannot get a string back. That's the interface of monoid, right? So here, when we join handle pizza and handle nukes together, we get a new effect. And then we just run it, final effects. So we first extract the effect out. At this point, this is the same thing, right? So this is an effect that has some user input and some final effect. When we execute it first, we execute the user input, right? Which includes the user inputs for all those things composed. And then we take the final effects and we execute that in one go. So this is what our code will look like. This has no boilerplate, right? This is literally as little as we can get. Well, that's wrong. You can also go smaller. I still don't like it. Okay. So this pattern is very common, right? This is, again, something where you have an effect that returns another effect. Nested effects. In Haskell, anytime you have a monad, which may not just be effects, could be other things like state, right? When you join it together, when you have nested effects, you have an operator called join, a function called join, that will extract the inner effect out and execute that also. This is fundamental to monads in Haskell, right? So you can just do join, and that's it. So join you can think of as a run effect thing, right? Okay, moving on. So this has no boilerplate. You can't go lower than this. Who agrees? You can't. So I'm going so you write your effect, join it together, and then you can do inline, right? Or you can also do this mapend does the same thing but with lists. So you can take a list of effects, and instead of calling that spaceship type operator, you can call mapend, which takes a list and joins them together. So if this becomes very, very clear. All right, requirements change again, right? We have a condition on whether we want to execute everything at the end or not. That depends on the user input that we got. So here, only when you've agreed to both ordering the pizza and launching missiles do we want to do both. Otherwise, we don't want to do anything, right? So just like we had an earlier condition where if you can order if you ordered a pizza only then launch nukes, here it's the other way around also. If you've not launched nukes, then we don't want to order pizza also, right? So it's a condition that includes all the effects, okay? So then again, we're back to the same situation. There's no way to write this using monoids, right? We're stuck. So, but then we try to look for patterns here, right? So I'm going to move slightly faster. In case you don't understand it, please stop me or talk to me later on. But this part looks like business logic. This part looks like boilerplate, right? We're getting user input. Then there is some business logic here which says, okay, if both of them are true, then do something. And then this is again boilerplate where I'm saying execute both the effects together. Can we abstract that further? So this is what we have a pattern. We again want to do it on an arbitrary number of effects. We want to ask some questions. We have a function called validate, which takes all those answers, decides whether or not to run the entire effect. You can think of it like an installation wizard, right? So it will ask you, okay, do you have valid directory? Do you have enough space? Do you want to install this component? Do you have this prerequisite installed? Only if everything validates, you gave the right answers to everything, then it will proceed with the installation, right? So you can think of it that, instead of my crazy example, you can think of it as a more practical thing. Right, so how do you do it? We want, again, the same things. We want to be able to define flows separately, join them together, minimal boilerplate. We also want to be able to call a function before performing an effect to decide whether or not to perform the effect. All right, so we can't do it with monoids. I can tell you right now we can't do it with monoids because the captured user input, which was inside the closure, cannot be accessed outside it, right? So that's the problem with the solution we had earlier. But FP gives you granular abstractions, right? So monoids are too simple for us. They don't do everything. Monads are too complex. We don't want to do that because, again, it has that reordering effect. So let's work through this. How would you do it as an FP programmer, right? Even I don't know the answer when I started writing this. We didn't have the user input. from the effect, let's return the user input also. So we not only get the effect out, but we also get the user input out. You can think of it like a record that has two values. So our effectful functions, they return this structure, ret, okay, which we've defined here, which has an input, which was the user input, and an effect, right? And A here is bool most of the time, but we abstracted it out for reasons I'll go into later. Okay, so now all we have to do is return this scan order also. We're not just returning this effect, we're also returning the user input. Now, when we want to compose it, we first get the things out, then we check valid on the inputs, right? We're first calling input on the return values, calling validate function, and then we're doing the two effects. Again, we have to get the effect out. This is the analog to dot notation in Haskell. They're simple functions. Boilerplate. I don't like it. Okay, I don't want to do this. So again, what we want to do is we want to compose these effects together somehow, right? This is a general pattern called applicative in Haskell. Okay, applicative basically means if you have multiple effects, you first get the values out and then you perform a function on it, right? Which is a pure function. This is an applicative. When you start doing functional programming, you'll learn these patterns, right? Again, it's in the standard library. So what does the applicative instance for IO look like? It does what we want, exactly. Okay, it gets the things out, calls the function on the return value and returns that. Okay, so we try to use applicative. It doesn't work. Why? It doesn't work. Why? Because if we get the input out at this point to call valid on it, because valid only works on inputs, then we have lost access to the effect now. We are returning two things, right? We want to do two separate things. So how do we do it? So we dial back. We basically say that we first get the effects and get the return values using applicative notation. Then we check the validity using again applicative notation. This also works. And then we do the effects. I hate this code. Because we have so much code for composing two things together. Imagine if we had 10 things, right? Again, the same problem. So now we are looking at this part of the code, right? This checking for a condition and doing something is a common pattern, right? So we abstract this by, and here the insight is that this has a condition, which is a Boolean, which is like user input, and then some effects to run, right? This is exactly our ret data type that we defined, right? So then we define a function called run ret, which takes a ret, which has some Boolean condition, which is the user input, can order pizza, should order pizza, and then some effect, and then when the condition is true, when the user said yes, then we run that effect. So we define a function like this. So we abstracted a little bit. We did run ret here, right? But now we need to compose a run ret at this point. So I mean, I can write it, but it's doing more work, but it's not. I'll tell you why. Because this thing, using applicative notation, can compose a ret, right? I may be going a little bit fast, but just assume that it can do that, right? A person who has been working with this will look at it and say, oh, what if this returns a ret instead, right? So then we define an applicative for ret, which does what we want, which does that thing, and then it becomes this simple, right? This applicative notation returns the ret that we want, and we can just run it. Slightly simpler, right? Assume that it works, take my word for it. Now we see another pattern, two successive applicatives. Applicatives compose. When you're doing one effect and then you're doing another effect, and you're doing both in the same way, that you are doing multiple effects and then composing them together with a pure function, then that can compose. So we compose these things together. So the first one does applicative on IO, on effects. The second one does applicative on ret, which is again effectful, because at the end it has to run an effect, right? So we have two effects. We define a type called flow, which does both IO and returns a ret, because we have to compose those two things together. And we define an applicative instance for flow, okay? For this flow. Turns out we don't have to write it. The standard libraries already have something called compose, which can take any two functions, any two functors, and join them together, right? So this works for applicatives also. So we basically say that our flow is basically a composition of IO and ret, right? Once you've defined it like this, then we already get this applicative instance, which you don't need to understand it. All this says is that if both the constituents, the IO effect and ret are applicatives, then the combination is also an applicative. And what this basically means is that it will use the applicative instance for the constituents and combine them together. This is already written for us. And we define a run flow, which basically calls run ret, right? Once we've done this, then we define flows in the normal way, but we wrap it in compose because that's a new data type, and it's otherwise exactly the same. And then this is what it looks like right now. This is what the code turns into, right? So it's doing so much stuff. You define these things separately, right? And then you say, I have business logic here, right? You join them together with these operators, which are standard operators. For someone who's not used to them, they may look like, lots of complicated code, but to any Haskell programmer, they are very, very familiar, right? You join them together using standard operators, and it does exactly what you want. This has no boilerplate. Then you can run it, obviously. So we've composed this valid and the operator soup that we have here. It's composed a new effect for us, a new ret, and we can run it. A new flow, and we can run it. This has no boilerplate. This truly has no boilerplate, so I'm not going to go further. We're running out of time. But takeaway, functional programming is not just for functions, not just for pure code. You can take imperative code. The flexibility that it gives us allows us to manipulate those things in ways that you would not think, would not be as apparent to you as imperative programmers. But it truly results in reduction in boilerplate, truly results in zero cost code reuse. All the stuff that we saw is zero cost, right? This is exactly what normally you would code, the code that you would write, you're calling it in a different way. That's it. It's entirely zero cost. So this is where we were. Side effects. Don't worry about side effects. Okay? Side effects fit perfectly well within FP. And this is why Haskell is the world's best imperative programming language. Thank you. I'll take any questions if you have them.
So since we have many languages over there, so to build what kind of applications we use this Haskell?
So Haskell, I hate this way that people say it, but Haskell is a general purpose programming language. I hate it when people say that because it doesn't give you a lot of information. But Haskell, the things that Haskell is really good for, that in my experience, are web frameworks, web programming, right? User interfaces, concurrent and parallel programming. Haskell has best-in-class libraries for all these things, right? So it's being used for distributed programming a lot. And those are the killer use cases. But otherwise, it's a general purpose programming language. You can use it for anything.